This work presents model-based evaluation of recall-based interaction techniques. This is work done by Julien, Gori, Bruno, Fruchard, and Gilles from CNRS and INRIA. I'll leave you with my good friend Lisa for the rest of the video.
Recall-based interaction techniques are interaction techniques that leverage user memory. For example, in keyboard shortcuts, the user has to remember an arbitrary mapping between commands and key combinations. Marking menus is another well-known example of recall-based interaction techniques. In the novice mode, the user can exploit visual information to select the appropriate command, but in expert mode, the user has to rely on memory only to perform the right gesture. There exist standard experimental protocols to evaluate recall-based interaction techniques. Usually, these protocols consist of interleaved training and test phases. These phases may sometimes occur over several days. The number of training and test phases, the number of trials per phase, the duration of the breaks in between phases all affect the evaluation of recall-based interaction techniques, and we refer to these parameters collectively as the schedule of the experiment. We can take a closer look at a training block. In a training block, each trial consists of learning an association between a command and its trigger. During this time, a teaching method is available. During test phases, the teaching method is not available. For each trial, a stimulus indicates which command should be selected by the user. In this example, the user responds to the cut stimulus with the appropriate gesture for a successful recall. The average recall rate for a participant can be computed by averaging the recall scores, and this can be done for each testing block. This is then usually averaged over users, which gets us this typical bar chart that you will find in many evaluations of recall-based interaction techniques. One difficulty with such an evaluation is that indirect comparisons are difficult to perform. Let's consider two simulated experiments. In Experiment 1, two RBITs A and B are compared using a particular schedule, while in Experiment 2, the same recall-based interaction technique A is paired with a different recall-based interaction technique C, and both are compared with a different schedule than in Experiment 1. In both cases, we simulate outcomes of a classical experiment, obtaining bar charts of recall rates. When we analyze the results of these simulations, it is straightforward to perform direct comparisons, that is comparing A with B, and A with C. However, indirect comparisons are much harder, because the schedules used for evaluation are not identical, meaning the recall rates cannot be directly compared. It is difficult to tell which of B and C was more efficient, and it is also difficult to compare whether the two A's have similar performances. This last point is important when A is a baseline used for comparison, and we'd like to ensure that A has been implemented equivalently in both studies. The main idea of this work is to use model-based evaluation, where instead of comparing recall rates which are prone to various misinterpretations, we fit a model of memory to observe data and perform comparisons in the model's parameter space. The assumptions of this method are that user recall behavior can be described by a mathematical model with some parameters, that each recall-based interaction technique is associated with true parameter values, and that the user model is a function of these parameters and of the schedule. The first step of the process is then to select a recall model. In this work, we considered an exponential forgetting model due to Ebbinghaus. The model relates the recall probability for a particular association to two schedule variables k, the number of times the association was seen called the repetition number, and d, the time since the last association was seen, called the delay. The recall probability is also a function of the two memory parameters alpha and beta, which indicate how fast we forget, and how strongly memory is reinforced when a pair is learned again. Once the model is selected, we estimate the parameter values from observed recalls using maximum likelihood estimation. This allows placing the various recall-based interaction techniques in the parameter space independently of the schedule used to evaluate them. Because we are able to estimate their uncertainty, we are also able to actually compare these recall-based interaction techniques. Here, we see that both A's overlap and are not significantly different, while B and C are different from each other. So, one of the advantages of model-based evaluation is that it facilitates indirect comparisons between interaction techniques evaluated by different schedules. Another advantage is that it is insensitive to differences in execution times between recall-based interaction techniques. For example, let's consider 3 recall-based interaction techniques, which are strictly identical from a memory perspective, but which have difference in execution times. When evaluated on the same schedule, these differences in execution times add up and change the length of the experiment, and thereby change the delays between 2 identical commands. The result is that there are differences in recall rates, even though the interaction techniques were identical from a memorization perspective. This problem does not occur in the model-based evaluation, and all 3 recall-based interaction techniques are correctly identified as equivalent. A final advantage that we show in this work is that model-based evaluations help designing better schedules. Here we illustrate how the difference between 2 interaction techniques may be observed for different schedules. When there is not enough learning, the recall rates stay close to 0 throughout the experiment. When there is too much learning, the recall rates jump to perfect recall, which again makes the comparison difficult. What we need to do is find the right amount of learning that best discriminates the 2 techniques. To do so, we propose a method to compute the informativeness of a schedule. We namely show that the schedule that best distinguishes 2 techniques in the model space also best discriminates 2 techniques in the recall rate method, meaning our information measure transfers to the classical design of recall experiments. The surprising finding we observe is that we predict it is optimal to increase the spacing between training blocks in a way that keeps the recall rate constantly at around 20% for each test block. In summary, our model-based evaluation facilitates indirect comparisons of interaction techniques that exploit user memory, is less sensitive to distortions due to differences in execution times, and facilitates schedule design. We also propose a Python library to help you engage with the model-based evaluation for recall-based interaction techniques. The Python library is hosted on Python's package index and can be installed directly from Pippy with a simple command line. With PyRBIT, you can simulate various experiments assuming exponential forgetting or ACTR models of memory. In both cases, we provide code for worked-out examples. With the library, you can also evaluate the informativeness of a schedule, and even perform simulation-based power analyses. This library will help you design better experiments to evaluate recall-based interaction techniques. We invite you to read what's in the paper, where we provide a lot more details and evaluations, a link to a repository for all the code used in this paper for full disclosure, and discussions on how to generalize the approach to more complex models of memory and in cases where data is incomplete. Thank you for watching this video. If you want to understand what the magic is behind model-based evaluation, stay tuned for this technical appendix video. In our work, estimation of parameters is performed via the well-known maximum likelihood estimation method. This method generates point estimates from observed data. It works by defining the likelihood of the observed data. The likelihood is defined as the probability of observing this data, given a particular data model, which in our case is a memory model, the parameters of this model, and the schedule. The method of maximum likelihood estimation then works by finding the parameter value that maximizes the likelihood. This produces a point estimate, that is a point in a 2D space. The theory of maximum likelihood estimation also allows to compute uncertainties. It exploits the fact that asymptotically, meaning for a large number of samples, the estimate follows a Gaussian distribution centered around the true value. That means that if we were to replicate the estimation procedure and plot a histogram of all point estimates, we would find they align nicely into a Gaussian. This in turn means we can compute confidence intervals by using standard confidence intervals for Gaussian random variables. In this case, because the parameter space has 2 dimensions, we have multivariate Gaussians, and so covariance matrices rather than variances, and confidence ellipsoids rather than confidence intervals, but the intuition stays the same. The inverse of the covariance matrix, which is called J, which measures the spread of the data, is called the Fisher information in statistics. You can understand why it is measure of information when you see how it affects confidence intervals. The more information the sample provides, the tighter the confidence intervals. This covariance matrix can actually be computed from the likelihood itself, as the negative Hessian. The Hessian is just the multivariate extension of the second-order derivative. So this J will serve as our measure of information. The only problem we have is it is a matrix, and we'd like a single number. So what we do is we compute the square root of the determinant of J, and this is our measure of information. The justification for this is found in the paper. To wrap up, how do we exploit this to measure the informativeness of a schedule? Well, we can simulate an experiment with n trials, and replicate it r times for a given memory model. Then we can compute the average J for each replication, and compute the cumulative sum to have an increasing information as the schedule unfolds. Of course, we use our information measure rather than J to have a single dimension number. The computations of likelihood gradients and Hessians computed for the exponential forgetting model and the ACTR models can be found in the supplementary materials of this work. Our paper also shows how we validated the entire estimation procedure, and also how to generalize our approach.